Good evening, everyone, and welcome to this session 6 of this course, Measure and Integration. So again, we'll solve few questions from the last session. Then I'll recap all the theory that you have learned this week, and then after that, some problems based on that. Okay. So starting with this problem session. So let's start with this problem. Okay. So did any one of you check? Try to solve this problem. Yeah. Okay.
Sir,
Yeah.
I am trying, but it is not completely. I am able not completely to prove it.
Okay. So how did you try to solve this problem?
Sir, it is given that Fn is a pointwise integral over fx. We can interchange integral, and it is a finite. So
Over x.
for any measurable set, it is a subset of x. Yes, sir. So any measurable set, it is a subset of x. So by the properties of the integrable function, the integral of fn over e, it will be less than the integral of fn over x, and also the integral of f over e, it will be less than the integral of f over x.
Okay.
So if we take limit of the first inequality, so limit of the integral of fn over e, it will be less than the limit of a integral of fn over x, and it will be nothing but the integral of f over x, which is a finite. So it is implies that the limit of fn over e is a finite. So implies that limit of the integral of fn over e exists.
Okay, so this shows that limit. Okay, just a second. Limit of integral fn over e exists, right?
So this implies that the limit superior and the limit inferior of fn over e, all of them are equal if it is exist.
Exactly. Yeah.
So by Parto's lemma,
okay, so from here what we got is limit integral of fn over e is less than equal to integral f over x, right?
Yes, sir.
Okay. Now tell what you got.
So then we apply the Parto's lemma, the integral over e. So the integral over e of a limit infimum of fn du, it will be less than limit infimum of a integral over e fn.
So you are talking both sides e.
LHS is equal to f because fn converges f2 pointwise.
Right.
So sir, and RHS is equal to limit infimum is equal to limit n tends to be infinity of the. So if also we prove the converse, so the inequality becomes equality. So the reverse part, sir, I am not able to prove the reverse part.
Yeah, actually you are correct. Okay, so this step, this till here, it's very meaningful that okay, somehow we can make sense that okay, limit of this thing will exist. Okay, so this is correct. Okay, but okay, let's see whether this will be useful or not. I am a bit doubtful whether this will be true or not. But okay, so far whatever you have said is actually correct. Okay, so let me just repeat what you said. So okay, so I don't think you need this one, right? So far. Okay, so you don't need this one so far. I feel so. Did you use anywhere? No. Okay. So the first thing is okay. So to make sure that limit exists. Okay, so this was my your first step. That okay, the limit. So fn over e is less than equal to fn over x, and so the limit. Okay, so one more thing. Actually, there is a flaw. Flaw in the sense when you take limit here, you actually say that the limit exists, right? Okay, so when you are taking limit, somehow you know that the limit exists. So this is a wrong statement. I mean, here you cannot do so. Okay. Did you understand why this is wrong?
Yes, sir.
So here what you are proving, so what you have proved is assume limit exists. Okay. And then you have proved that this limit is finite. That's all you have proven. That you assume limit exists, and then you have proven that if it exists, then it is finite. That's all you have proven. Okay.
Yes, sir.
So this is something that will not help us, right? Because what we have to first show that this limit exists, right? So this part you are somehow assuming that limit exists. That's why this is not correct. But what you have said here is totally correct. Okay, so let me just rub it off. Okay, now let me copy this one. Okay. So maybe I can put it here. Okay, so what you are saying that this okay, you understand, I hope everyone understand that f of e is nothing but f chi with e over x, right? This is what it means, that f over e. Okay, I hope this is clear to you, this thing at least. Okay, so let us try to solve this. Okay, so you know, so let me rewrite this somehow. Okay, so to be more precise, so let me crop this up, let me bring it down. Okay, so this f over e is nothing but x f chi over e. This is the function, right? Now this is nothing but, as she mentioned, that this is nothing by, so you can use, okay, you can write one more line if you want. So what you can write is, you know, it's given to you that fn converges to f pointwise. Okay, so this will be used here. So I mean, so this would imply fn chi of e converges to f of chi of e pointwise. I mean, it's not required to be written, because it is just well understood that this is a trivial statement that I have written over there. But okay, anyway, so this is f of chi. Now as she mentioned that this is nothing but, this is equal to lim inf of fn. Okay, so this is over x lim inf of f n chi e. Okay, just by this thing. Okay, now this is, so this is basically equal to limit, and limit since exists, so this is lim inf of this thing. And now by Fato's lemma, this is lim inf of fn of chi e, right? And then n going to infinity. And then what we can do, okay, so this I have already written. Okay, so this lim inf of this thing, now you already know. Okay, so what else is given to you? So fn of chi e, yeah, so this is nothing but limit okay, so limit n tending to infinity x of, sorry, over e, right? So over e you can write f of n. So this is one thing what we have got, right? That limit of this quantity, this is f of e over e, is less than equal to this limit of this. Okay, so how can we make sure that the limit exists? That we are not sure, right? Fn given there of e. Okay, so again, Okay, so just now let me assume that okay, limit exists. Okay, so this side, as she said, this is just exactly that statement, assuming that the limit exists. Okay, now as she was saying that she was not able to do the reverse part. Okay, so for that what you can do, you can deal with the complement of f. Okay, I mean, you are integrating here over e. Now you can deal with the e complement. So let me explain how it works. So you already know that this f over x, I can write it f e plus f e complement, right? This I can do because they are disjoint. This e and e complement are disjoint, so I can write integral of f over x as this. Okay, now the way we have dealt with f here, we can deal with f complement, f over e complement. Okay, so if you want to rewrite this, you can even rewrite f of e complement is nothing but f over x minus f over e. Okay, so let me number this as 1 or 2. Let me say this is 1. Okay, and then what you can do now, again similarly the way you have done for e, so similar to 1, just using Fatou's lemma, similar to 1, what you can write is integral f over e complement is less than equal to limit n going to infinity f n over e complement, right? This you can write in the same way. Okay, okay, so this I can write. So this is my second. Okay, not second, so let me use this second here. So using second, what I can say is this is nothing but f over x minus f over e. This is less than equal to limit n going to infinity this f n over x minus f n over e, right? And this is nothing but, so I'll just, I mean, throw the limit in both the things. So it will be limit n going to infinity fn over x minus limit fn over e. Okay, and this you already know, then this was given to you, that this is nothing but f over x, right? So you knew this thing. Okay, sorry, not here but this one. Okay, so this says that this is f minus lim of fn over e, right? Now you know that this is finite, it's given to you, right? You can see here, so that this is very important, that the integration of f is finite over x. So that is why, since it is finite, I can cancel it. So this I can do cancellation just because they are finite. Otherwise it will be infinity minus infinity case, so we cannot do that. So this is finite, so we can cancel, I mean, we can subtract from the this identity, or sorry, inequality, and then what we are left out with, minus f. So what we are left out with is this minus f over e is less than equal to limit fn over e with minus sign. Now if you multiply by minus, it will be reversed. So what you have is f of e is greater than equal to limit of fn over e, right? So this was the first inequality where you got that integration of f over e is less than equal to this limit fn, integration of fn, right? Here you are getting the reverse thing, integration f is greater than equal to this limit of integration of fn, right? So let us call this as 3. So using 1 and 3, what you get is limit integration of fn over e is nothing but integration of f over e, right? So the main thing was that this part you just use the Fatou's lemma on the set E. Here what you have to do, you have to use the Fatou's lemma over E complement. Okay, and then you will get the result. Okay, now the question is how to say that this limit exists. Okay, that is crucial part. Okay, so let me think how we can do. So this is lim-inf. If I do it in a similar way, okay, so let me just think. Okay, so this was my, okay, if I don't write this, I was getting this lim-inf. Here if I repeat the same thing, I'll get this here lim-inf, right? I'll get lim-inf. So lim-inf I'll get here. Here lim-inf will be there, here lim-inf will come, here lim-sup will come. So minus lim-sup, minus lim-sup. So lim-sup here I'll get is greater than lim-sup equal to, yeah, I think I can do, just a second, lim-sup of fn over e, f over e is then equal to f over e less than equal to lim-inf of, yeah, I think this is fine. Yeah, okay. So what you do, so I'm not assuming this limit exists. Okay, so let's forget about this line. So I'm saying, so let us write it as lim-inf n going to infinity, this is e fn, right? This is my 1. So what I have got is integral f over e is less than equal to lim-inf of integral fn over e. Okay, okay, now if I apply it here, what I get is integral f over e complement is less than equal to lim-inf of fn over e complement, right? This thing just by 1. Okay, I'll get like this. Now here if I do this, the similar thing, so this will be f over x minus f over e, this limit infimum, this will be lim-inf n going to infinity, this difference fn x minus fn e. Now if I distribute this lim-inf over both the things, so I will get lim-inf here, and here I'll get lim-sup, right, just because of the minus sign. So I'll get here lim-sup, right? So here also, and we know that this particular thing is converging, so this will be converging to, this lim-inf will be equal to the limit, and that will be equal to integral f, and here it will be lim-sup. Okay, so this is lim-sup. So here I'll get minus f over this is less than, sorry, this is lim-sup of fn, right? So again, if I do the multiplication with minus sign, I will get lim-sup here. Okay, so now if I combine this, so what I get is lim-sup over fn of fn over e, okay, is less than equal to integration f over e, and by 1, so this is by 2, by this 3, and this is less than equal to lim-inf, okay, of fn over e, right? This was there, so this is by 1, so this is by 1 and this is by 3, right? And this, you know, lim-inf is always less than equal to lim-sup, right? So this is lim-sup of fn over e, right? So by this, okay, so we'll do a bit of shifting. Yeah, so now if I combine this identity, you can see this is on the left hand side, this is on the right hand side, it's the same quantity, so this is actually an identity. So what we get is this lim-sup of integral fn over e is equal to lim-inf of integral fn over e, and this is equal to integral f over e, right? Hence, since the lim-sup and lim-inf are equal, this means that the limit exists. So this implies limit over e fn exists, and the limit fn over e is nothing but integral f over e. Is this clear, or do you have any doubt? Do you want me to
Yes,
repeat?
sir.
Everything is fine, right?
Yes, sir.
So this proof is basically 3 step, okay, nothing special. So just use Fatu's lemma over E, you will get an inequality. Use Fatu's lemma on E complement, you will get another inequality in terms of limso, and then you just combine them, you will get that. You will get the answer. So it's just 3 step using Fatu's lemma twice, once on E, and the next time you apply on E complement, you will get limso limins, and then you will get this sort of inequality, and then you are done. Okay, so if there is no problem in this question, then let us proceed further. Okay, so this is it says that you know that the monotone convergence theorem is true for the increasing function. This question is saying that if instead of using this assumption, so you assume the assumption fn increasing, okay, and fn, okay, non-negative was there, and fn, okay, and fn converges to f, right? Then you said that integral fn converges to integral f. This is all you had. Now the question is that if it's decreasing, then will it be true? Okay, so this is my conclusion. These are my assumptions and conclusion. So the question is, does this conclusion hold? Is this true? So the answer is no. Okay, this will be true under certain condition, and the condition is that if you are given that integral of fn is finite for some n naught, let's say for some n naught in n, then this will be true. Okay, in general this is not true, and this is the counter example for that. Okay, so the counter example is this one. Consider this function fn. Okay, I think I left something, right? Okay, here there was one more part, I just remember. So this part, you showed that this fn if converges to f over x, this implies integral fn over e will converge to integral f over e for all e belonging to the sigma algebra of measurable set. Okay, that's all you can say. But this was true when this integral of f was finite, right? Now the question is, will it be true when they are infinite? Okay, and you can clearly see where we have used this fact. We used this fact when we had to cancel this one. Okay, so the question is, will it be true if this is infinite? And the answer is no, it will not be true, and I will show you how. Okay, so this is the counter example for that. Okay, so consider this function. Okay, so what you want to make sure? You want to make sure that this integral f and limit of integral fn over x, okay, this should be infinite. Okay, that is the first thing. And then you have to show that this f over e is not equal to limit fn over e. Okay, so you have to find fn such that this thing hold. Okay, so let us consider this function. Okay, so it is just this, you take anything like chi of minus infinity comma 0. Okay, so on this real line you have the whole support. Okay, and then what you do, you just add something which will be very important for this particular thing. So you add any interval, okay, which is not fixed, which is depending on n. So you can clearly see this is not depending on n. This is to make sure that this is infinity always. Okay, so this particular thing is making sure that this integral of fn is infinity always. So the limit is also going to be infinity, and the function to which it converges should be of will also include this function, right? So the integral of f is also infinity. So this particular thing is making sure of this condition, okay, that this will be holding. Now what you have to make sure, over the set E of the limit function is not equal to the limit of integral of fn over E. Okay, so let us first define fn, and then I'll say you what E you can choose. So suppose this is my function chi of n comma n plus 1. Okay, now if you choose this function, you can clearly see this fn, this function is converging to chi of minus infinity comma 0, and this part will go to 0 because as n is becoming large, this n comma n plus 1 is becoming large and it's going to infinity, so these two are becoming same, so this will be the limit function. So is this clear that this fn will be converging to this one? It's pretty easy, right?
Yes, sir.
So this is the limit function. Now just calculate this integral. Okay, now what you need to make sure that this e must not be this one, right? So this is your f, so let me name this. So this is your limit function. Now if you integrate over something over here, you'll get some non-negative value. Okay, so what you do, you choose e which is disjoint from this, so better you choose 0 to anything, I mean whatever you want you can choose here. Okay, so you can choose, let's take the most, that's 0 infinity. Okay, when you choose e to be this one, what will be the integral of f over e? What will be it? It will be 0, right? Because after 0 the function is 0, so this is the integral. Now if you want to calculate this integral of fn over e, right? So this fn on this set is just this quantity, I mean, so this is the only thing which will be integrated, because this is, I mean, this function is 0 basically in this part. Okay, so this integral over fn over e will be nothing but integral over n comma n plus 1 of the function 1. So this is the Lebesgue measure, this one, right? And this is nothing but 1, right? This is the length of this interval, which is 1. So you can clearly see that the limit is going to be 1, where the function f, the integration of f is 0, right? So this is not true, I mean this is true, that they are not equal. Okay, so this is the counter example for this part, when the integral are infinity. Okay. Okay, so now this was the second question, that whether the monotone convergence theorem hold for decreasing sequence or not. Okay, so let us see the example where this does not hold. Okay, so try to construct this function, consider this one, that fn of x is equal to what you can take 1, and x is greater than equal to n, and 0 when x is less than n, or just else otherwise. Okay, so it says that after n the function is taking value 1 and it is 0, so you can clearly see. So what are the fn? The first thing is that, okay, fn are non-negative. Fn's are decreasing as well, right? This is clear, I mean the function is not decreasing, but the sequence, although, yeah, so the sequence fn, the sequence is a sequence of decreasing function, so decreasing sequence of functions. Okay, and also you can clearly see that this function is converging to 0, right? After, because till n point, till here the function is 0, and after this is 1, but as n goes to infinity, this is going to infinity, so I mean this part will not be there, so the function fn converges to 0. Okay, pointwise. Okay, so this assumption is true, so all assumptions are true. Okay, now is the conclusion true? Let's see. So integration of fn, okay, integration of fn over let's say whole r, yeah, so let's take over whole r. So these functions all are for all x in r. Okay, so okay, so this integration of fn over r, what will be that? It will be infinity, right? For each n So if you want, I can write further. So it is from n to infinity 1 dx, or if you want to write in terms of Lebesgue measure, let's write n infinity dm1, and this is nothing but infinity, right? Now so this implies that the limit of fn over r is infinity. But what is the limit of integral of f over r? This is 0, right? Okay, so the f is this function. So this limit I am saying f. So this is my f. So the limit function integral is 0. So clearly this is not true. So the conclusion is not true. So this implies, this collectively implies that limit integral fn is not equal to integral f. Okay, so hence we prove that, okay, we have a sequence of function for which all the assumptions hold true, but the conclusion is not true. Okay, but what I said earlier, that this will be true when any one of the function has limit integral finite. So as you can see, all the functions fn's have integral infinity. Okay, and this is the root cause for this not to be true. So let us go to the next question, where it says that you assume this condition. In general, you can even replace this condition by fn naught finite for some n naught. So here in particular you are choosing n naught to be 1 in this problem, but you can do it for if it's finite for any of the n naught, any of this number n, then that is good enough. Okay. So did you try to solve this problem? No? Okay, so let us see this problem. So now the first thing is that you know that the function f1, integral of f1 is finite. Okay, but you don't know the function is pointwise finite or not. Okay, but you know this result, that integral of f1 finite implies f1 is finite almost everywhere. This you have already seen, I guess. If the integral is finite, this means that the function is finite almost everywhere. Okay. So let us say E is the set x belonging to x such that f1 of x is infinity. So this is of measure 0, because of this thing what I wrote above. Okay, so what you can do, so by okay, I've written measure 0. Okay, so now what you can do, so why I am writing this whole thing, so f1 of x. Okay, so why I am writing this thing? So the first thing, let me give you a sketch of the proof what I'll do. Okay, so here you have been given that fn is decreasing. Okay, if fn is decreasing, you can clearly say that fn is increasing, minus fn. Okay, then can you use mct on this fn, minus fn? So suppose this is my gn, can you use this mct over here? Can you tell me whether you can use or not?
Sir, minus fn then pointwise converges to minus f.
Right?
Yes, sir. Then we can apply the.
No, we cannot, right? Because see, in the condition, in the assumption of monotone convergence theorem, you assume that all the functions are non-negative. Okay, so this is a problem. You cannot use. So you cannot use. So what you can do instead, you know fn is decreasing. Okay, you know minus fn is increasing. You only need to make sure somehow that, okay, so we have to consider some function, some sequence which is so increasing as well as non-negative. You have been given this one condition, that this fn's, so this is something like this, right? f1 greater than equal to f2 greater than equal to, and so on. Now if you consider f1 minus fn, this is always greater than equal to 0, right? So now consider your gn to be f1 minus fn. Then this is non-negative, right? This is increasing, and in fact it converges to f1 minus f, right? Is this fine, whatever I said here?
So we're fixing the first term, F1.
This is
the
fixed
greatest
function,
term.
right? So f1 is fixed, the sequence is given to you, so f1 is fixed.
Okay, sir.
Yeah, so consider gn equal to f1 minus fn. These are non-negative, these are increasing, and these are, I mean, this converges to f1 minus f. Now you can apply MCT, right? So by monotone convergence theorem, this integral of f1 minus f fn, this, okay, so if you want you can write in terms of limit. So limit f1 minus fn is equal to f1 minus f, right, over x, right? Now here why I was writing all this story, see, here the problem will arise when f1 is infinity. What if fn is also infinity? Okay, so instead of writing this x, what I'll write, that this, instead of x I'll write e complement. I mean, okay, so what I mean is, let's write x, okay, but this is meaningful because this is equal to limit e complement f1 minus fn, because when we consider the integration we don't need to consider the measure zero set, right? Because you know this theorem, right? So if e is of measure 0, then integration of f over x is nothing but integration of f over e. So this is there. Now you know that e is of measure 0, so this integration is 0, right? I wrote something in the last session that if the function is 0, then the integral is 0, or if the set over which we are considering the integral, if that is of measure 0, then also the integral is 0. So this is 0, so this is only over e complement. So whenever we talk about integration, we only consider if we can ignore the set which is of measure 0. Okay, so that's why since e is of measure 0 and e is the set where the function f1 is infinity, so that we can ignore. So in that sense this is sensible. Okay, yeah, in that way this and this, both the things are sensible. Okay, now you can just distribute the limit. So limit over f1, sorry, f1 is independent of n, so this is x over f1 minus limit x over fn minus f1 over x minus integral f over x, right? Now you know this quantity is given to be finite. The integral of f1 is given to be finite here, right? So you can cancel them off. So this you can cancel. So what you get is limit fn over x is equal to f over x. Okay, so you understood where we use this condition f1. And the moment you say, suppose instead of f1 say f of some k naught is given to be finite, everywhere you can replace f1 by f k naught, and you can consider this sequence n greater than equal to k naught. Okay, you just consider that sequence. In the limit it doesn't matter, right? So you can do the same thing for any k naught. Okay, is this fine?
Yes, sir.
Okay. Okay, so if this is fine, now let's proceed to the theory part. Okay, so this is just the definition of integrable functions. So we say that any complex valued function, measurable function, is integrable if mod of f is integration of mod f is finite, right? And when we write mod f, if it's complex value, it is nothing but real part of, so yeah, so mod of f is nothing but root under real part of f square plus imaginary part of f square. Okay, and we know this is a non-negative function, and for that we know what is the notion of integration. So integration of x, or I mean integration of this over x is nothing but, we'll take a sequence of simple function, we take not sequence, but the definition is like this: supremum 0 phi less than equal to f integration of f over x, right? This is the definition. Yeah, so this is the notion of integration of non-negative function. For general complex value function, this is the notion. Okay, this is how we define. So okay, now if it is integrable, then the notion of, then the integral f over x is nothing but, this is for real value, but for complex value this is integration of the real part plus iota integration of the complex part. Okay, now what is the integration of real part? Integration of real part is nothing but integration of positive part plus integration of negative part. No, I think there is some typo, so this should be minus this minus. Okay, so now you have integration of positive minus integration of negative part, integration of positive minus negative. Okay, so this is just to recall you the notion of integration. Okay, so you learned this DCT, dominated convergence theorem, right? So till now you have just learned one convergence theorem, which is the monotone convergence theorem, and then one very important lemma, Fatu's lemma. Okay, and this is the third third convergence theorem, which deals with sequence of function and interchanging of limit and integrals. Okay, so suppose this fn is a sequence of integrable function on x such that this fn converges to f pointwise. Okay, this is the first condition. The second condition says that mod of fn is less than equal to g, where g is some integrable function. Okay, and this is non-negative. So from here only you can say that g is greater than equal to 0. Okay, so this g is non-negative, and the extra condition is that g is integrable, that the integration of g is finite. Okay, so under these two conditions you can say that the integral fn is also converging to integral f. Okay, so here this point fn converges to f, and mod of fn less than equal to some g, integrable function g, will imply that integral fn converges to integral f. Okay, so what I was saying, that these two conditions, that fn converging to f and mod of fn is bounded by some integrable function, will imply that the integral also converges to the integral of f. Okay, so this is what DCT says. Okay, and here we don't need to consider that this non-negative thing here. Okay, so this is the most general theorem, and even this theorem has a further generalization, which I think I'll state somewhere. Okay, so it is there. Okay, so this is the theorem that this is called L1 convergence. Okay, so you will get to see later on that you will see L1's LP space. Okay, because this is nothing but the norm of fn minus f, L1 norm. So this says that fn converging to f almost everywhere, and this boundedness thing will imply L1 convergence. Okay, so so far you can just understand that, okay, this is also something which is called convergence. This is another, so it's called convergence in mean, I think, in this lecture or this book. Okay, so this convergence in mean is equivalent to this convergence of integral. Okay, so now the next question is, what you have seen that pointwise convergence implies this integral convergence. So is the converge true? Suppose this integral fn converges to integral f, can you say that fn converges to f? almost everywhere? Answer is no. Okay, but what you can say, that there exists a subsequence such that this subsequence converges to f almost everywhere. Okay, so the converse of this dct is not true. In convergence of integral does not imply the convergence of the sequence, but there will exist a subsequence which will converge to the function f. Okay, but okay, so but what you can say, okay, I think that should be stated somewhere in the next slide. So instead of saying this almost everywhere convergence, this thing, you can say that if the integral converges to f, you can conclude that fn converges to f in measure. Okay, this you can say, and if you can say this, then from here only this will follow up, that the subsequence converges to f point almost everywhere or pointwise. Okay, so I think that will be stated properly in the next slide, few slides. Okay, so this was all about dct. Now this boundedness of this sequence mod of fn, this is very important, and this is what next example will show you. Okay, so consider this function, this sequence of function fn over this natural number. Okay, then this integral of fn, so you can see, you can clearly see that this will converge to 0. Okay, and in fact this will be uniform in this space, with this discrete space. Anyway, you don't need this uniform also. For now you can forget about this also, but what you can see, that this fn converges to 0 pointwise, that is clear. Okay, the way the function has been defined. The next thing is, what is integral of fn over x, right? So as I have mentioned, that this integral is nothing but the summation, right? So this is summation fn of k, where k belong to the natural number, and this is nothing but, since after n this is 0, so this is summation k equal to 1 to n fn of k, because after that is 0. I mean, the rest of the things are 0. So here what fn of k is nothing but 1 by n. So this is something fixed. So 1 by n, and this is k equal to 0 to n. So 1 by n I can take outside, because this summation is over k. So 1 by n, and then summation k equal to 0 to n, and then 1. So I mean, we are summing 1 n number of times. So this is n, right, this summation, and hence this integration is 1. Okay, so this integral of fn is 1, while since the limit function, this is the limit function, right, this limit function is 0, so the integral is 0. So this clearly do not coincide, and the reason being, so here you can clearly see that this fn converges to f, but integral of fn does not converge to integral of f. The reason being that you cannot bound this fn function by some L1 function. Sorry, I should not say L1. What I should say is some integrable non-negative function. So the reason being, this is the conclusion. Okay, and the reason for this thing is, that mod fn you cannot bound, so there does not exist g, so integrable g, such that mod of fn is less than equal to g. Okay, that is the reason for this failure. Okay, so that's why this condition is very important. Okay, yeah, so as I was saying above, that does this integral convergence implies pointwise convergence, and the answer, as I said you earlier, that is not true. But what is true is this one, that suppose you know that this, yeah,
sir, how we will say that there does not exist a g, such
okay,
that
in this
mod
example
fn
you are
is
seeing,
equal to g?
so
How
okay,
do you
so
conclude that there does not exist such a g?
okay, so let us see this graph of this function. Okay, suppose this is 0.1 and at here the value is 1 something fixed, right? So 1 by n, 2 1 by n, 3 1 by n, I mean the same values, right? So if you want
Yes,
to
sir.
bound this function, okay, suppose you want to bound this function by g, then obviously g should be greater than equal to 1 by n.
Yes, sir.
This is clear to you? Now if you want to integrate this g, this will be greater than equal to this summation 1, I mean, okay, let me not write directly, but this is g of k 1 to n, and this is greater than equal to 1 by n. So this is 1 to infinity, n equal to 1 to infinity, and this is greater than equal to 1 by k, and this is divergent, right, this series?
Yes, sir.
Is it fine?
Okay, sir. Okay.
Okay. So, okay, maybe. Okay, so maybe I can. Should I put it? Okay, I'll see if I put it. If I can put somewhere or not. Okay, so it's clear to you, right? Yeah.
Yes, sir. It's clear.
Okay, so now coming to this point, that this integral convergence, does it imply pointwise convergence or not? As I mentioned, that this integral convergence will imply convergence in measure, okay, but and from here you can clearly conclude that there exists a subsequence such that f and k converges to f almost everywhere. This is by one of the theorem what I mentioned like in during the session which dealt with this notions of convergence. So convergence in measure implies there will exist a subsequence which will converge pointwise, okay. So from here there you can conclude this one, that the subsequence converges to f point almost everywhere. Even you can find an example also where this integral fn converges to integral f, okay, but you cannot say, you will see that fn does not converge to f pointwise, okay. So that is also there, okay. Okay, just a second. Okay, fine. Yeah, so even you can find an example where the convergence is there, that integral fn converges to integral f, but fn does not converge to f pointwise. Okay, so this is the generalized dominated convergence theorem what I was talking about earlier. So as you saw in DCT, that what was the condition, that this was there, that fn converges to f pointwise, okay. This is the extra condition, okay. So here f should be integrable, so that is an extra condition, okay. I think this was not there in general DCT, right? So in general DCT you just had fn converge, so let me write it here, fn converges to f and mod of fn converges is bounded by g. From here only you can conclude, so this implies f is integrable and integral of fn converges to integral of f, okay. But here you have to assume a priori that the function f is also integrable, okay. And the second thing is that mod of fn x, so this is something that you assume, something extra, but here you get some relaxation. What is the relaxation? That this fn, mod of fn, is bound now, not bounded by a sequence of, I mean not just bounded by a fixed function, but it is bounded by a sequence of function gn, okay. But with this gn will have some property, that property is that gn should be integrable and it should converge to some non-negative integrable function. So earlier instead of this you had this g where g was integrable, so here you had this condition. Here you are saying that this mod of fn is bounded by gn, where gn is converging to this non-negative integrable function g, okay. And also you have to assume that this integration also converges, you don't just need this. So here gn converges to g and this integral gn converges to integral g. If you have both of these, then you can conclude that integral fn converges to integral f, okay. So this is called generalized dominated convergence theorem. Okay. Okay, I hope this statement is clear. Okay, if it's fine, then let's proceed to this notion of absolute continuity of measure. So this says that suppose you have two measure in your hand, then you said that one of the measures, so let's say you have mu and mu tilde. Okay, you say that mu tilde is absolutely continuous with respect to mu. Okay, symbolically it is represented in this fashion: mu tilde absolutely continuous with respect to mu if mu tilde of E is equal to 0 whenever mu of E is 0. Okay, so this thing you will see later on in detail. Just for now you can just understand this definition, that if this is 0, the measure of some set with respect to this measure is 0, that should imply that mu tilde of E is also 0. Okay. Okay, now this is the theorem which says that suppose you have a measure space, and if you have an integrable function, then for any epsilon you can find a delta such that the measure of this set, okay, so I mean delta with some set E. Okay, so for any given epsilon greater than 0 there exists delta and a set E. Okay, so not one set but for all set E. So for given epsilon there exists a delta such that for any set E with measure less than delta, the integration will be small. Roughly what it means is that suppose so if you have any epsilon greater than 0, then the integration of this is, if you want to make it less than epsilon, okay, then there will exist a delta. I mean it's just continuity sort of thing, that for any epsilon there exists delta greater than 0 such that this integral will be less than epsilon if the set, so this integration over some set, okay, so let's say E. Okay, so for any epsilon you can make this integration small, okay, such that the set over which we are considering the integration, that is also small. Okay, so the integration is of a small size if the set over which we are considering the integration is also small. So it's something like this. So I mean if you want to understand in terms of Riemann integration or anything, so suppose this f of AB, okay, so suppose everything exists, this integration. Now if this b minus a is small, is very small, then that would imply that the integration over this AB interval is also very small. That's it. I mean something like this. Okay, so this is there. This is true for any integrable function. This is statement that if you have an integrable function, then if you make the domain smaller, the integration will also be smaller. Okay, so you can make the integration very small if you make the domain over which we are considering the integration small. I hope this statement is clear. Is this fine? Okay.
Yes, sir.
Yeah, so this is another example. I think I showed you something like this in the last session, that if the measure of E is 0, suppose this is 0. Okay, so the first thing is that I have shown you that if this is the measure mu, if you are starting with a measure space, then if you define a function like this, then this nu is also a measure. This I have shown you, right? This is also a measure. In fact, if the measure of this set E, if mu of E is 0, then you know this implies that this integration is 0, right? And this implies that nu of E is 0. So this says that nu is absolutely continuous with respect to mu. Okay, and using this also you can say that, say you can make this very small, making this E small, right? So using this theorem also you can say something like that, that this nu of E is small if mu of E is small, right? So mu of E small means that the integration is small, and this implies that this is small, mu of E. I mean, if you don't want to go in this way, you can just, I mean, this theorem is clearly saying, this theorem clearly says that this nu is absolutely continuous with respect to mu. Otherwise, this is the best thing. I mean, this is the best argument to say that this is absolutely continuous with respect to mu. Okay. Okay, if this is done, then let's come to the comparison of this Riemann integration and Lebesgue integration. So in fact, any function, okay, on a bounded interval, okay, so for Riemann integration you learned about this AB only when A and B are finite, and for integration of this sort you learn using the limit function, that limit B into infinity AB. This is how you define Riemann integration. So this is definite integration, this is indefinite, right? So this is how you define. So we are just concentrating on this bounded interval. So if you are on bounded domain, then you know how to define Riemann integration. It's just by upper sum and lower sum. So if you have a function which is defined on a bounded interval, okay, and this function is also bounded, and suppose that this is bounded, then f Riemann integrable would imply that f is Lebesgue integrable, and in fact both the things, that Lebesgue integration of f will be equal to the Riemann integration of f. Okay, so the value will also coincide. Okay, so this theorem just says that if you have a function, real valued function defined on a bounded interval, and the function is also bounded, in that case the Riemann integration of f is equal to the Lebesgue integration of f. Okay, so if the function is Riemann integrable, that function is Lebesgue integrable, but the converse is not true, and this you saw in I think in last session. So you know this example, right? This example is coming since the first session. So this function is not Riemann integrable, but you know that this function f is 0 almost everywhere, and so it is Lebesgue integration, and the Lebesgue integration over 0 1 is equal to 0, but it is not Riemann integrable. Okay, so this shows these two things, this theorem and this remark shows that the set of Riemann integrable function is strictly contained in the set of Lebesgue integrable function. Okay, and this is what I was saying in the very initial stage, that we want to extend the notion of integrability. Earlier we just had Riemann integration. Now we can extend this, I mean, this set of Riemann integrable function a bit. I mean, we can increase the size, and that size is this Lebesgue integrable function. Okay, so the notion of integration, what we define, okay, is generalization of Riemann integration. So this state inequality, this identity says that Lebesgue integration is generalization. I mean, generalization I am saying just because if a function is Riemann integrable, then it is Lebesgue integrable, and the value matches. That is the important point, that the value matches, and that is why I can say that the Lebesgue integration is generalization of Riemann integration. Okay. Okay, so this all thing is for the compact set, or maybe for this bounded interval. Okay, it's, I mean, so I should not write this clearly. So this has some certain condition. Okay, so I have just written it symbolically, but this actually include bounded functions. Okay, and here also bounded functions. So to be more precise. Okay, so maybe I write plus bounded functions. I mean, this is in the condition. So this example is to say that this domain, what we are considering, that has to be bounded. So you can see this example where the domain is unbounded. Okay, and this is the function sin x by x. You can check that this function is Riemann integrable, and you have to use some complex analysis tools. Okay, that theorem, what is called? What is that theorem? Some using this poles and all this thing, right? We evaluate this type of integral, some fz dz, residue theorem, right? So there is theorem, residue theorem. From there, I think you can conclude about integrability of this sin x by x. Okay, and this Lebesgue integrability, and you can check very clearly if you consider this mod of sin x by x. Okay, so in this 0 infinity, you can break it up. So n to n plus 1 pi mod sin x by x. Okay, and then you can remove this x by maybe 1 by n plus 1 pi mod sin x n to n plus 1 pi. Okay, so there is summation. So I'm just writing it, I mean, briefly. So you can dominate this mod by this function, right? So everywhere I'm talking about this Lebesgue integration. Okay, but the moment it comes here, this Lebesgue integration and this Riemann integration can be interchanged because we are in the bounded domain, and in fact this is a continuous function, so it is bounded. Okay, so we can switch from Lebesgue integration to Riemann integration, and now here you can evaluate this integral and this. Okay, so this summation is here. Now you can integrate this, you will get some value, because this, since this sin x is same in this interval of length pi, so the integration will be same. So it will be some constant summation 1 by n plus 1 pi, also you can take outside, so it's some constant times this, and this, you know, this is divergent. So in that sense you can clearly see this is not Lebesgue integrable, and in fact it is not, and you can also show that this is Riemann integrable. Okay, so this was an example to show that this condition is important. Okay, so this is an equivalent condition for Riemann integrable function, that if a function is Riemann integrable if and only if it is continuous almost everywhere. Okay, so this is in the context when we are in the bounded domain and the function is also bounded. So under these conditions, the function is Riemann integrable if and only if it is continuous almost everywhere. Okay, so the point of discontinuity, I think you saw this in real analysis also, not exactly this line, but something like this, that f is Riemann integrable if and only if f has countably many discontinuity points. Right, you have seen this theorem, right, in real analysis when you learn this. Yeah, so this is generalization of this theorem. Here you just say that it has the set of countable points has to be countable set. Here you are saying countable set means measure 0 set, implies that it is of measure 0, but this is saying much more, that integrability implies and is implied by if it is continuous almost everywhere. So the set where it is discontinuous is of measure 0. Okay, so this is another application of this in theory of Lebesgue integration, that you can prove this Weierstrass approximation theorem. Okay, and what it is, that every continuous function on a compact set can be approximated using the sequence of polynomials. Okay, so you can prove this theorem using this theory of Lebesgue integration. Okay, now I'll just outline the differences and similarities of this measure theory and probability theory. In fact, both are, the probability theory use the tools of measure theory. Okay, in fact it is measure theory except a few things, and because of that few things we cannot say that probability theory is subset of measure theory. So these two things are separate, but you can use measure theory to study probability. Okay, and this is how you do that. So the sample space, suppose you denote by omega, and suppose this collection of event okay, that will form a sigma algebra by definition. Okay, so this is from the theory of probability. I'm saying that if you have a sample space and if you consider the collection of events, that has to be a sigma algebra. Okay. So the collection of event has to be a sigma algebra. So this, the probability space denoted by this omega, b and this p. P is the function which calculates the probability of an event. Okay. So the only condition in general for a measure for the studying measure theory, okay, what you have is x, some s and some measure. Here you have the same thing. Okay, this is your x in some sense, this is your sigma algebra, and this is the measure. But the difference between this and this is, I mean, this is a particular example. It says that the measure of the whole set omega should be 1. Okay, so that is something which is very specific to probability theory. Okay, so when you consider a measure space in general, you do not put any condition on what is the measure of x. It could be infinity also. If you consider x to be r and mu to be the Lebesgue measure, then you know that the measure of the real line is infinity. Okay, but that is a measure space. But for that to be a probability space, the mu of x should be 1. Okay, so probability space is a subset of measure space. Okay, the space of measure space is large and the probability space is much smaller in that set. Okay. Okay, so this is there, and this measure of a is just the probability of event a, what I mentioned out here. And so you know something about conditional probability. So conditional probability of a, which is denoted by this. So this is the way you calculate in probability theory. Okay, in terms of measure theory, this is nothing but this new measure pb, okay, defined on this sigma algebra. Okay, and this is the definition, and this definition is nothing but conditional probability in the theory of probability. Okay, so this is analog, I mean the analog of conditional probability measure theory in general. I mean, this is the general thing. This you can do for any sigma algebra over any set x. So this thing you can define for any x as mu, right? But this will be conditional probability if this mu is a probability measure. Okay. So far it seems that everything, the property of this probability is nothing but everything is coming from the measure theory and nothing else. So it seems that probability is nothing but if you know measure theory, you know the probability, but that is not the case. So okay, so it's the same thing what I was saying. So it's another notion that if two events are independent, if this conditional probability and the probability is same, this is from the probability theory. Okay, and in terms of measure theory, you know that this conditional probability is nothing but this quantity. Okay, this one, and if you put it here, if you replace that, you will get this thing. So in terms of measure theory, this is what independence means, that a and b are independent if probability of or measure of a intersection b is equal to measure of a times measure of b. Okay, in terms of measure theory. Okay, and this, okay, random variable x, so this is, I mean, this is a term from probability theory. So random variable is nothing but a measurable function defined on omega. Okay, so do not confuse with what I was writing earlier, that this x as mu, when I write it in this fashion, this x was the set. Here this x is a measure. Okay, so do not confuse this x with this one. Okay. Okay. Yeah, so this was about random variable, and this is the terminology coming again from the probability theory. which is called expectation of x, and this is nothing but integration of x over omega with respect to the measure dp. So this is integration with respect to measure p. Okay, and again similar to the notion almost everywhere convergence or pointwise convergence, in probability theory they called almost surely convergence, and this convergence in measure is called convergence in probability. Okay, so far what you have seen is the similarity between these two things. Now what you will see is something which only probability theory have but measure theory does not have. Okay, so the most important thing is this function. So try to understand this function ft. So this function measures this set. Okay, so this f of t is nothing but measure of this set. Okay, so if you consider this function f, so given two random variable, so suppose you have x and y, so if corresponding to this you have function fx, corresponding to this you have function fy. Okay, so these are two functions which we call distribution function, okay, of random variable x and y. Now there could be chances that these two things are equal. Okay, when they are equal we say that x and y are identical, but in measure theory we do not talk about if. So this is something like you have two functions. So as I said earlier, that random variable is nothing but measurable function. Okay, so in measure theory, suppose we have two function f and g, and corresponding to this f and g, if I have this capital F and capital G, if they are equal, we don't have anything notion calling that f and g are identical in measure theory. But in probability theory it is very useful thing that this identical distribution. Okay, so this is something which is very specific to probability theory, and also this independent thing, that two random variables is called independent if they satisfy this thing. So again this is nothing but, as I showed you earlier, that a and b are independent if p of a intersection b is pa times pb. So it's the same thing. Okay, so it's written the same way, but we don't talk about whether two functions are independent or not in measure theory. But in probability theory it becomes very important that whether two random variable, whether they are independent or not. Okay, so these two terms, independent or identical, these are very specific to probability theory. Okay, which is not in measure theory. You can define, but it is meaningful in probability theory. Okay. Okay, so this was all about the theory part. Now let us try to solve few exercises. Okay, so let's start with this first problem. So this is about calculating integral of this thing. So this is just the Riemann integration. So you have to compute what this integral would be. Okay, so let me do it quickly. Just calculation and nothing very specific. Okay, so let us see what this integral is. A infinity. So n upon 1 plus n square x square. Okay, so this is dx. You can clearly take n outside. So this is nothing but a to infinity. So this is 1 by 1 plus n square. So nx whole square maybe. Yeah. So now you can do change of variable. So take y equal to nx. If you take this, if you do this substitution, what you get is y. Now x was varying from a to infinity, so y will vary from an to infinity. This is 1 by 1 plus y square, and this dx is nothing but 1 by n dy, right? So this n will cancel. So what you have is this n a infinity and 1 plus 1 by y square dy. This is tan inverse y, and this is na to infinity. So tan inverse infinity, you know, this is pi by 2 minus tan inverse n of a. Okay, So till, I mean, in this question this a was given to be in R. Okay, now, so there will be different cases, right? You know the tan, how tan behaves. So so let us deal with three cases. So the case one is when a is equal to 0. Okay, case 2 when a is positive. Okay, and case 3 is when a is negative, right? Now when a is 0, you can clearly see this tan inverse is of 0 is 0. So in that case this integration okay, so this is going to be just pi by 2, right? And if you take the limit of n also, then also, since the RHS is independent of n, we'll get pi by 2, right? Now the case when a is positive, okay, so this a infinity, if you take limit, so this is pi by 2 minus limit n going to infinity and tan inverse of na. Now when this a is positive, this will go to infinity, n of a, and tan inverse of infinity is pi by 2. So this will be pi by 2 minus pi by 2, which is 0, right? The third case is when a is negative. In that case this will go to minus infinity, right? And tan inverse of minus infinity will be minus pi by 2. So in that case, what you have is pi by 2 minus, and again minus pi by 2. So you'll have pi, right? So I hope this is clear. This was just an easy computation, nothing very hard. Is this fine?
Yes, sir.
Okay. So now let us try to see this example. So this is something which tells you that this integration and this summation cannot be interchanged. So you can clearly see this cannot be interchanged, but it can be interchanged under certain condition, and the condition is that this should be finite. Okay, that this quantity. If this was finite, then you could have done that. So this is just a counter example to that thing. Okay, I think I mentioned such thing. I don't remember whether I mentioned this for this thing, right? That integration of summation you can interchange when, say, when fn was non-negative. Then you can prove this using MCT. Okay, but you can even do it for general function under the condition that this, if you consider this mod of fn, this should be finite. I hope I am correct. So there is some condition, and I hope that that condition is this one. So under that condition you can interchange this one. Okay. Okay, so this is a counter example to that one. So let us try to see what the first one. Again, this is also just calculation and nothing very specific. So this is 0 to infinity fn of x dx, 0 to infinity. This is a e minus n ax minus 0 b b e minus n bx, right? So this is, you just take a outside, so this is dx dx. Okay, and then to 0 to infinity. So what you can do, you just again do, so this is a you take outside, sorry, so a you take outside, this is integration is nothing but e minus na by minus na, right? Okay, so I am just writing 0 to infinity, but okay, so I'll just write once. After that I'll not write in this fashion. So as you know that Riemann integration is defined in this fashion: b going to infinity and b, right? So this is the way how you define this Riemann integration when the domain is unbounded. Okay, again then minus b limit, so let's write y limit y going to infinity. It's e minus nx, e minus nbx by minus nb 0 to y. Okay, so okay, so now substitute y. So the first thing is, let's take minus na outside, so this a will cancel out, so what I have is minus 1 by n. Okay, and then limit y going to infinity e minus n a y, and then we have this 0, so e 0 will be 1. Okay, then minus, again similarly we will have, so here we will have plus 1 by n, and then limit y going to infinity e minus n dx, sorry y, and again you will have at 0 it will be 1. Okay. Yeah. So now, so this plus 1 by n will cancel with this minus 1 by n, so eventually this term will go away. What you have is this one. So as y goes to infinity, so here a is positive, right? So, and b is also positive. So this a, since a is positive, b is positive, as y go to infinity, this is going to be 1, right? So this whole quantity, this whole quantity will go to 0, right?
0.
Yeah. So as y goes to infinity, this will go to minus infinity upper thing, then this will go to 0. This is minus 1 by n, this is 0, and then plus 1 by n, this is 0. This is going to be 0. Okay. Okay. So this integral of fn is 0. So if you consider the summation also, n from 1 to infinity, integral 0 infinity fn of x, this is dx, this is going to be 0. Okay. Okay. So now let's go to the second part. So you have to calculate the integration of the mod. Okay, so let's see. So 0 to infinity mod of fn x dx, which is okay. So what is this fn of x? Let us see what mod will be. Okay, so it's a e minus n a x, and then minus b e minus n b x. Now it's given to you that a 0 less than a less than b, right? So suppose so if you want to understand in particular, you can take a to be 1 and b to be something 2, let's say. So as x becomes large, so as you increase the value of x, this will decrease faster, right? Just because this b is greater than a, right? So this will decrease faster. Okay, and that is why this whole term will be greater than equal to 0 for large x. Is this clear to you? And this is because of this condition. First tell me if this is clear or not. What I am saying that this exponential of minus nbx, okay, since b is larger, this will decrease. So you know that e of minus kx, okay, will go to 0 as k goes to infinity, right? What I am saying, suppose if I do k square, then this will, I mean not k1 k square, but let's say k1 and e minus k2x, both thing will go to 0. But if k2 is equal to, let's say, 2k1, I mean it's larger, then this will go to 0 faster, right? Because you know exponential grows, and if it's minus, it will decrease. Okay, so if you yeah,
If the x is also negative,
sorry, can you repeat?
x is also negative, so it will not converge to the 0.
No, x is positive, right? We are in 0 infinity.
Oh, okay, that is it.
We are in 0 infinity, right? So what I am saying that since b is larger, so this quantity will go to 0 faster. Okay, and that's why this term, I mean this term will dominate this one, and eventually it will be positive after certain stage.
Yes, sir.
Okay, now what I'm saying that after some point it will be positive, and before that point it will be negative. In that case, when x is small, this will dominate because of this coefficient b. Since b is larger, so this coefficient will dominate this coefficient. Okay, I hope it's clear to you. I mean, I'm saying it vaguely, but actually you can prove it, that how this, so you can do one derivative test and two derivative test. I mean, so you can find f1 prime of x where it is 0. So suppose at this point and this point, suppose something like this you'll get, say here decreasing, here increasing, I mean something. So you can actually get this thing. Okay, it's not difficult, but what I'm saying is just natural. I mean, this is something which you can just conclude by looking at the function. Okay, so what I'm saying, since b is larger than a, initially when x is small, this quantity will dominate, and for large x this quantity will dominate, because this will go very fast to 0. Okay, I hope you're convinced from this argument, right?
Yes.
Okay, if this is fine, then what I am saying, so it's clear that this will be greater than equal to 0 for large x. So now the question is where it is. So suppose, so you can actually calculate, so fn of x naught is 0 for some x naught belonging to 0 infinity. Okay, you can check, actually you will get some value of x naught that I am not calculating. So I mean, just I'll, maybe if you want I can sketch. So you just do this thing, that fn of x naught equal to 0. If you substitute, this will say a e minus n a x naught equal to b e minus n b x naught. Okay, and then you will get e minus, so you will get e n b minus a x naught equal to b by a. Right, so and then you can just use logarithmic log functions. You will get log b by a, and x naught will be 1 by n b minus a log b by a. Okay, so okay, I have calculated it, but this is the way you can calculate this x naught. Okay, so fn of x naught will be 0 at some, so I mean, I don't know whether I should write x naught or not, because this x naught is depending on n. Okay, so it's better not to write in this fashion. Okay, so far we are not considering the summation, so at this level I can write that x naught. Okay, if you want you can put an exponent here if you want. Okay, so x naught of n, so this is x naught of n. Okay, so you'll get something that fn of x naught is 0. So this, so why I am doing this, because I want to split this one. So 0 infinity mod of fn x dx, now I can write in 0 to x naught. Okay, so actually you can prove all this thing, that in 0 to x naught it will be negative, and after x naught it will be positive. So I have given a vague argument to, I mean, justify this calculation. So 0 infinity can be broken in 0 x naught point, and in this region the function is negative, so I can write minus of fn x dx, and in the region x naught to infinity the function is positive, so I can just write fn of x dx. Okay, okay, now this is, so let's substitute the function. So it was a e minus n ax minus b e minus n bx, so it's minus sign, so let's minus plus, and here we have, sorry, it's 0 to x naught, and here you have x naught n to infinity a e minus n ax minus b e minus n bx, okay, dx. So now if you calculate this 0 to x naught n, okay, so here again so minus a e minus nax, if I integrate I'll get minus a e minus nax by minus na. So this a will cancel, so it will be e, so it will be e minus nax upon n, and this will be e of minus nbx by minus n, right? So here it will be minus n. Yes, so this will be plus, okay, so 0 to x naught n, and again if I calculate this one, what I get is e minus nax by, so this is plus a, so it will be minus na, and here you will have b will be e minus nbx by, sorry, a will not be there, and here minus will be this plus, so I mean this will be, so this will become plus, right? Don't know whether I'm doing correct or not. I don't know, it should be just reverse. So here both of them are plus. Is it correct or not? This will be plus, this will be minus, okay, now this will be, then this will be plus, okay, and this is from x naught n to infinity. I hope all the calculations are correct. B then minus, okay, I think it's correct, okay. Yeah, so now you can just now substitute, so what you get is e minus n a x naught n, so 1 by n I can take common, okay, so let's substitute x naught n, so e minus n a x naught n minus e minus n b x naught n, so this is for x naught. At 0 if I put, I'll get 1 here and 1 here, that will cancel, so okay, so I'm just leaving that thing. Here what we have is, so at infinity both, so let me take 1 by n common. Now at infinity this is going to 0, this is going to 0, so that part is gone, and for at x naught n I'll have with minus sign, so with minus sign I'll have e minus n b x naught n minus e minus n a x naught n, okay, so what I got, yeah, so now let me just combine them, so 1 by n, let's just e, so this will be 2, so this will, all these things will add up, right? So it will be 2 by n, and now e minus n a x naught n minus e minus n b x naught n, okay, so these are all the terms that we get at last, okay. Now if you want, you can substitute that x naught n, so if you see here that n times x naught n, okay, so let me write it here, yeah. Oh, sorry, yeah, so what I was saying, that we will get this thing here. Now what I'm saying, that n times x naught, if I want to write from here, this will be 1 by b minus a log b by a, right, which is, I mean, which is not depending on n, so right hand side is independent of n, okay. So this n times x naught n, I can write some constant, so let me write this some constant depending on ab, so c of ab, I mean c ab, something like that, so got, okay, so let me put it here somewhere, so this I'm defining c of ab So now I can write 2 by n, okay, E minus A times CAB minus E minus B times CAB. Okay, so overall this whole thing is another constant which is depending only on A and B. So together I can write C tilde A comma B and then 1 by n, right? So I am combining all this 2 and all this thing. So this whole thing I am calling as C tilde of AB. Okay, so now now you can sum. So you have to sum this whole thing, right? So you have to calculate summation of this integration. So now if you sum this whole quantity, summation 0 to infinity mod fn, I guess, yeah. So 0 to infinity mod of fn, this is greater than equal to C tilde AB summation 1 by n, and you know this is infinity. Okay, so this is infinity, so this is infinity. So I mean this, so this is done, that this integration, summation of integration of mod fn is equal to infinity. Okay, okay. Okay, so what was next? So the next was to show that this summation of fn is in L1, and if you integrate that value, that will be log of b by a. Okay, so let us see what this summation is. Okay, so the C part, so this is summation of fn, and this is nothing but a e minus n ax minus b e minus n bx. Okay, so you have to sum this from 1 to infinity, right? Now so let's say this is e minus ax raised to the power n 1 to infinity, and then minus b summation n equal to 1 to infinity e minus bx raised to the power n. Okay, now this is a, and this is a geometric series, right? So if you fix some x, this is nothing but a geometric series of real number, so you can sum this. So you have, you know the formula, so this is the first term upon 1 minus the difference. I mean, so this is the formula, right? So a n is nothing but a upon, sorry, so it's like n equal to 1 to infinity, so it's a1, right, n, so it's a1 1 minus r, where r is the, what's geometric ratio, I guess that is the name. I don't remember the name, but this is the geometric difference. So this is ar, so a2 minus a1, so an plus 1 minus an is nothing but r. Okay, so using that I can write this as e minus x. So here the geometric difference is also e minus ax, and the first term is e minus a, and here also sorry, it's e minus x. In a similar way you have this again, e minus bx upon 1 minus e minus bx. Okay, now so this is a, and now what you can do, so now maybe just let's take this in the denominator, so it's e ax minus 1, right, minus b 1 minus, sorry, e bx minus 1. Now so this is integration, this is summation. Okay, now you have to check whether this integration is defined or not, and what is that integration. Okay, so let us see this 0 infinity 1 by e ax minus 1, what is this value of this integration. Okay, so now what you can do, again you can do this change of variable y equal to e ax minus 1. If I do, so what will I get? So it will be 1 by y, and then if you do dy will be e ax a times dx, right? So this will be a y plus 1 dx. So dx is nothing but 1 by a 1 plus y dy, Okay, so this is 1 by a, 1 by y, y plus 1 dy. Okay, okay, so what will the limit? So if x is 0, y will be 0, right? So at x equal to 0, this will be 1, and 1 minus 1 is 0, and at infinity it will be infinity, so the limit will be same. Now this is 1 by a, and this 1 by y into y plus 1 can be written as 1 by y, and then minus 1 by y plus 1, right? So now if you write in that fashion, so you'll get, if you integrate log of mod y 0 to infinity minus log of mod y plus 1 0 to infinity, right? So, and if you substitute, so okay, before substituting, maybe let's try to write in this way: mod y upon y plus 1 yeah, okay, so then you can do 0 to infinity. Okay, so for infinity case, okay, so let me first substitute this x thing. So what was y? Y was e ax minus 1, right? So it's e ax minus 1. So we can remove the mod because y is in 0 infinity, so it's positive. So and here y plus 1 is e ax, right? And again the limit will be same, 0 infinity 1 by a, then what else? Okay, so now maybe you can break this. So 1 minus e minus ax 0 infinity. I hope I am doing everything correct. Oh, okay, so far we have considered just one integral, right? So let me combine this, both the integrals. So can you do this part by your own, or should I write all the calculation? What do you want? Tell me. I mean, it's just calculation. Okay, so okay. So maybe I'll write. So this is a times this is 1 by, what was that? E ax minus 1 dx is nothing but log of 1 minus e minus ax, and then this is 0 infinity. Okay, so at infinity it's clearly 1, I mean, because it's 0, because at infinity this will go to 0, this will be log of 1, and log of 1 is 0. Okay, so this is 0 minus, at 0 if you put, this is going to be log of 0, which is not defined. So maybe I can write it as limit, what should I write, z going to 0 1 minus e minus ax. Okay, so till now we will put it in this way. So it's 0, okay, so if you want, you can do. Okay, so this is the integration of this thing. So this quantity we have found what this value is for this one. So the summation of fn, so if you integrate 0 infinity summation of fn, okay, you will, the first quantity is this one, which is minus limit z going to 0 1 minus e minus a of z. Okay, here it should be z, and then the b, the second part b will give me, so it was minus, right? So minus minus will be plus, plus limit z going to 0.
So,
Yeah,
sir, it's limit z tends to 0, log of 1 minus
oh, right,
e raised to minus.
exactly. Yeah, thanks for the correction. So it is log, so it is log here, so it is log 1 minus e minus az. Okay, so now let's just combine both the things, so you can understand why I'm doing this, because you can clearly see this is infinity and this is minus infinity. So infinity minus infinity does not make sense, so we'll have to use some L'Hopital type of thing. So let us first try to bring it in the form of some known thing. Okay, so log, so this minus thing I can do it in this way, 1 minus e minus az. Okay, am I doing? Oh sorry, here it will be b, right? So this is due to b, so this is bz, and here 1 minus e minus az. Yeah. Okay, so again, if you now, since log is a continuous function, I can take the limit inside. Okay, so log of limit z going to 0, 1 minus e minus bz upon 1 minus e minus az. Okay, now if you take limit, it's 1 minus 1, which is 0 by 0 form, so I'll have to use L'Hopital, so I can use L'Hopital to get this limit z going to 0. If I differentiate it, what I get is e of bz minus bz times b. Okay, because minus minus will be plus. Here I'll get e minus az times a, right? So this will be the limit, and this will, oh sorry, so this will be nothing but this will be limit z going to 0, and then this will be, so if I put the limit, I'll get b by a, right? So this will be 1 and 1, so this is b by a, so this answer will be nothing but log of b by a. Okay, and this, okay, so this is integrable, this summation is integrable, and the value of integration is log of b by a. Okay, so this was just calculation, nothing very special, but this is an example where you can see that this interchange is not possible. Okay, so you cannot interchange this, but under a condition you can do so. Okay, so in the case of non-negative measurable function, you know that this is always true, that this integration is always true. Okay, so now I'll do this question. Okay, so maybe I'll just take 10 more minutes and then I'll stop. Okay, so this okay, so first try to understand this problem. So suppose this, instead of this condition, if I say you that fn converges to f almost everywhere, what is this theorem? I mean not theorem, but what is this identity? I mean, from where can you conclude this? So, can you tell me? I mean, it's quite easy. Yeah, this is just Fatu's lemma, right?
Yes, sir.
So Fatu's lemma says that lim inf of fn is less than equal to lim inf of fn when fn is non-negative. Okay, but when you put the condition that fn converges to f, this is nothing but integral of f, right? So it's just the, so if you have this condition, this is just the Fatu's lemma, I mean implication of Fatu's lemma, because in Fatu's lemma you don't have this assumption, this thing. Okay, so if you put this assumption here, then this is just a conclusion from Fatu's lemma. But here what's given to you is something different. It says that fn converges to f in measure and not almost everywhere or pointwise thing. Okay, so to start this solution, so the first thing what you should make sure, okay, that suppose this fn is not integrable. Okay, so I mean, so what I'm trying to say is that suppose this integral of fn is infinity after all the stages. I mean, for, so let me write it. So suppose, or let me write in this way, without loss of generality, there exists n in natural number such that integral of fn is finite for all n greater than equal to n. Okay, why I can write this? Because I know that suppose this is not true. Okay, then in that case this will say that integral of fn is infinity, and that would imply that this right hand side is infinity. that is not a problem, and that is obviously true, right? So if this is infinity for all n, okay, after certain stage, whatever stage you choose, if you get that, then this limit infimum will be infinity, and this is always less than equal to infinity. I mean, that is not a problem. So then that will be obviously true. I mean, there is nothing to prove. Okay, so that's why we assume, without loss of generality, assume such n exist. Assume there exists n such that this thing happen. Okay. Okay, so if I assume this one, now what I can do? Yeah, okay, so now you consider this quantity. Okay, this is just a real number, right? And it is nothing, it's coming from, so consider the sequence of this real number. So this is a real number, right? So this fn integration, that is a sequence of real number. So for lim inf fn, there exists a subsequence of this sequence fn such that, I mean, let me write the subsequence name also. So there exists a subsequence f and k of fn, sorry, this integration will also be there. Okay, so there will exist a subsequence such that this subsequence f and k, okay, this will converge to okay, so limit infimum of fn as n goes to infinity, and convergence means that the limit k going to infinity of this subsequence is equal to this thing. Okay, so this is just a property of limit infimum. Okay, so for limit infimum there will exist a subsequence such that which converges to this thing. So I mean, you just have to consider this sequence, okay, the sequence of real number. Okay. So now you have a subsequence whose integral converges to this quantity. Okay, now this fn k, okay, this fn k converges to f in measure. Why? Because since, okay, so this you have to prove. So this is a claim. Okay, maybe you can check this by yourself. So the claim is that this fn k converges to f in measure. Since, and the reason is you have to use this thing, okay, that fn converges to f in measure. So you just use the definition, you will get this. Okay, so assume that this claim is true, and you can check this. Okay, so maybe I should write check. So check this, that fn k converges to f in measure. Now since this fn k converges to f in measure, so that is why from here you can say that there exists a subsequence. So there exists a subsequence f n k j, okay, of fn k such that this f n k j converges to f almost everywhere. Okay, so for a subsequence we can do so. Okay, now so when you have this, you can even rewrite. So this is, let's say this is 1. Also this limit of j going to infinity f n k j, okay, this will be equal to limit k going to infinity f n k, okay, and this will be equal to this quantity. I'm just saying from here. Copy. Okay, so this is just because this fn kj is a subsequence of this thing. Okay, so the limit of this will be same as the limit of this. So this is not a problem, because if you have a convergence sequence, every subsequence will converge to the same limit. Okay, so let's say this is 2. Okay. Now, so these are the two things that you have. So now what you had to prove, that this f is less than equal to integral of f is less than equal to this. Now we will just use the Fathus lemma to conclude this. So this f, I can write it as limit j going to infinity f n kj, right? I mean this just by 1, so maybe by 1 right? Now this limit is nothing but the lim, right? So this is less than equal to lim j going to infinity f n kj by Fathus lemma. Okay, now what you can do, so you also know that this limit is also convergent. So this is nothing but the limit of j going to infinity, this f n kj, and by 2 you know that this is nothing but lim inf of by 1. Okay, and hence you are done. So is this fine to you? Is there any problem at any stage? I hope it is clear to everyone. Tell me if you have some doubt, maybe I can assist. So everything is clear to you?
Yes, sir.
Okay. So now let's proceed to the next problem. Okay, so this will be the last problem for today. So it will just be an application of this theorem. Okay, so what it says that when the convergence is in measure, then you have the implication of Fathus lemma. Okay, that's it. So we'll use this to conclude about this theorem. Okay, so this is the DCT theorem, I mean dominated convergence theorem, if instead of this pointwise you have this measure, convergence in measure. Okay, so the same conclusion holds. So this is some, I mean, okay, I will not write anything, but this is DCT analog to DCT type theorem. Okay, so instead of almost everywhere convergence, you have convergence in measure. That's the only difference. Okay, so let's start the solution. So what you have is that fn converges to f in measure, and from here you can say that there exists a subsequence. So there exists a subsequence fnk such that this fnk converges to f almost everywhere. Okay, now this implies that the limit of a measurable function is measurable. So this implies that f is measurable. Okay, so this f is measurable. So I mean the proof is basically the same as how we proved the DCT. So while proving DCT, we use the Fathus lemma. Okay, and so the moment we use Fathus lemma, instead of that Fathus lemma, we'll use this one. Okay, so the proof is nothing but the same as like the DCT proof. Okay, so from here we got that f is measurable. Now you also have that this mod of fn is less than equal to g, right? So this implies that mod of fnk is less than equal to g, and this implies if you take the limit you get mod of f less than equal to g, and this implies that integral of mod f is less than equal to integral of g, and which is finite. Okay, so this implies f is integrable. Okay, so these two are the first thing that need to be checked to make sure that this makes sense. Okay. Okay, so this was all about checking measurability and integrability of the function f. Now Okay, so for the proof file, you assume that all the functions fn and f are real valued. If it is complex value, so suppose f is equal to u plus iv, okay, suppose, then for u is a real value. So this, the proof what I'll give will follow for u. So okay, I will mention this at last. Okay, so now for the moment assume, so now assume or assume fn's and f are real valued. Okay, so now it's real valued. So what we have, so you had this inequality that mod of fn is less than equal to g. So this means that it is minus g less than equal to fn less than equal to g. Okay, so I mean on the whole space on x, this implies fn plus g is greater than equal to 0 and fn, sorry, g minus fn is greater than equal to 0. Right? So these two things you have. Okay, and also this fn's and g, all these things, if you want, so they are converging because fn, okay, so I mean it's better to deal with the subsequence fnk and not fn. Okay, so I mean it's better to deal with this fnk. Okay, so this is true for all n, but also, so I mean, let me write the conclusion. So copy, in particular we have this fnk and gnk. Okay. Also this fnk plus g converges to f plus g. Okay, almost everywhere. And this g minus fnk converges to g minus f, right? Okay. Okay, so now I can use the Fatou's lemma. How to use that? So this mod of f plus g, okay, so is less than equal to lim_inf of f n k plus g, right? This is by Fatou's lemma, right? And this is nothing but so I can write lim_inf of f n k plus integral of g. And okay, so what else I can do? So from here, so okay, so this was, so this is integral f plus integral g. Now we know that this integral of g is finite, so I can cancel it both sides. So what I get is integral of f is less than equal to lim_inf of integral of f and k. Okay, so this, let's say this is 1. Okay, now again using the second point, I can write integral g minus f is less than equal to lim_inf of integral g minus f and k, right? So from here I can get integral of g minus lim_inf of integral of f and k. And so from here, what again I can cancel this g, so I'll have minus, oh sorry, it will be lim_sup, right? So lim_sup of this, so here I'll have minus f less than equal to minus lim_sup of integral f and k, and if I multiply, the inequality will be changed, it will be plus plus, this will be, so this is 2. Okay. So from 1 and 2, what we have, so this lim_sup of f and k is less than equal to integral of f, and this is less than equal to lim_inf of f and k, and you know that this is less than equal to this, Okay, so this implies that limit of f and k is equal to integral of f. Okay, and okay, but okay, I mean I have written here Fatu's lemma, but actually it is not Fatu's lemma. I mean, oh, okay, okay. So it's better. So okay, so I don't want to use Fatu's lemma. Okay, so the mistake is, I mean, it's not the mistake, but it's from here what we have proved that the limit of integral of f and k is f, but we wanted to prove for limit of fn, right? This was our goal. So what you can do here, so instead of dealing with f and k, you deal with fn. Okay, so I think you don't this one. Okay, so also you have this, but it's not almost everywhere, so I completely forgot. So this is in measure. Okay, so you know the convergence in measure of fn. So from here you have the convergence of measure, and then this is not by Fatu's lemma. So by last problem, you know that this property holds, right? So this is by last problem, and everywhere it's not k. Okay, so it's fn, 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 fn. Again by last problem here also. Okay, so everywhere you have this fn, 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 and hence this is there. Okay. Okay, so what you here the only difference is that in the proof of DCT you use this almost everywhere convergence, but in this problem you use a theorem which is, I mean, of this sort. So Fatu's lemma, when you have this convergence in measure. Okay, so using that convergence in measure you can conclude about this result. Okay, so as I was saying about before about this one, so maybe let me mention. Okay, so this is when you have the function is real valued. So now suppose your function is of complex value, that f is of u plus iota v. Now you know that this un, okay, and fn is, let's say, un plus iota vn. So you know un will converge to integral u, vn will converge to integral v, since they are real valued. Okay, and hence so these two together will imply that integral fn converges to integral f. Okay, so that's why it's enough to consider just the real valued function and not complex value. Okay, so this was all for today. So I hope if you got all the points. Maybe now if you have doubt you can ask me.